In this video, we'll talk about the superposition principle and net force. And this is really just a review of what we did back in vectors. But the superposition principle states that the effect of multiple vectors, multiple forces acting on an object is exactly the same as one force acting on an object, which is the vector sum of all these other forces. So it simply says that if I have a force, like in this picture here, I have a force pushing to the right, and I have a force pushing upwards. As far as this person who is being pushed is concerned, she could have just had a force which was up and to the right like this, and that the effects would have been exactly the same. So these two forces here are exactly the same as this one force here, which is what we had, with vectors before. This is the x component, F1. This is the y component, F2. So there's a picture. This is called a free body diagram. We'll look at this later. There's a force this way. There's a force this way. I could have just as easily drawn one force off this direction. What might be more important, actually, is to be maybe given this force here and to realize, well, that's exactly the same as having one force like this and one force like this. And so we may be given the resultant vector and need to break it up into its components. Actually, this is more oftentimes what we'll need to do. It simply says the net force, which we actually say the net force acting on an object, is equal to the vector sum of all the forces. Vector sum of all forces. And the way we write summation notations, so we say here our F, the net force, is equal to the sum of all the forces. So this is the Greek letter sigma. It's an uppercase sigma, and it means to add up all of them. I'll use this notation often. So it's the sum of all the forces. So net force, sum of forces, same thing. A couple of little examples here. Let's say that we have, a box sitting on a surface here like this. Some of the forces that act on it are the forces that act on it. There's a weight acting down like this, W, and we also have a normal force acting up like this. These are opposite directions. If these are equal magnitudes, then the vector sum, we could say here the sum of the forces in the y direction, we'll focus on this being in the y direction, is equal to 0, right? Because these had equal magnitudes. And so the net force is 0. So this picture is equivalent to this picture here, in which there is no force whatsoever acting on the box. If these forces cancel, it's just like there not being a force at all. Same thing maybe if I had a box here, or actually let's say it's not sitting on a surface. Let's say we'll put it on a surface here. There's this, somebody's pushing on it off to the right. There's that F there. There's a weight like this, a normal force like this, and a frictional force, so it's back like that. Same thing is true this way. With the x direction, if we had the magnitude of this force F equal to the magnitude of the frictional force, we would have the sum of the forces in the x direction equal to 0. We also have sum of forces in the y direction equal to 0 if all these are the same magnitude, or at least these two are same magnitude, and these two are same magnitude. And then this would be equivalent to, again, this box just sitting here with no forces acting on it whatsoever. And like I said earlier, what we'll want to do is maybe we'll actually take this box and maybe we'll have, other than the weight acting on it and the normal force acting on it, and a frictional force acting on it, we'll have maybe a force like this, call this force 1, maybe another force F2, maybe yet another force F3, something like this. what we'll want to do is we will want to break it up into components. So we'll want to take this force and break it up into two forces, which are like this, F2x and F2y. And that'll be more helpful for us. Same thing with the F1, there'd be a force like this and a force like this. We'll want to break these up into components. But anyways, the superposition principle simply says that a net force has the exact same effects as the sum of all of the individual forces acting on the object.